Okay guys, here's a video on the cross product. So cross product between two vectors. So we got vector u here, magnitude 30, vector v, which is a magnitude of 20, and they have an angle of 40 degrees between the two vectors. So if we're doing the cross product, we can use our cross product formula, which is the magnitude of u times the magnitude of v sine theta. So if we do that, we do 30 times 20 times sine 40, and we end up with I don't know, it's like the same example I did in class. 30 times 20 times sine 40, 385.7. And this is a vector, so it'll need a direction. So if we use our right-hand rule, then we point our fingers in the direction of the first vector. So if you point your fingers in the direction of this vector, totally draw this, but I don't know how to. Well, you point your fingers that way, and then if you curl your fingers in towards vector u, then whatever way your thumb is pointing is the direction of your cross product. So my thumb would be pointing up. So I know my vector here, I don't know, there's different ways to represent this, but we could just, like the way the textbook shows it is like n hat, and using a positive vector to represent it going upwards. U and V are usually in the plane of your paper, say. You could also say that this is going outwards from this page. Okay, whereas if we would have done vector V cross, if we would have done vector V cross vector U, then if you're using your right hand rule and you pointed your fingers in the direction of vector V, and then you had to like curl them around, you'd notice that your thumb is going to point down, which means this vector would be U cross V, and this vector pointing down would be V cross U. So they create, it would equal the same magnitude, 385.7. But this time your direction vector would be pointing down. So your cross product would point down. 7 or 5.7 inwards to this page, from this page, whatever you want to say. So different ways to say it, as long as you get your point across. You could also sketch it out. And something else that's good to know is the cross product creates a vector that is perpendicular to both of the vectors, or a vector that's perpendicular to the plane that the other vectors lie in. Okay, so let's get a couple of algebraic vectors and calculate the cross product from them. So it's this crazy formula that you can watch my video on where I proved it. And an easy way to figure out the cross product is to do it in terms of our unit vectors, I hat, j hat, k hat. So if you write these out twice, I, j, k, and if we're doing A cross B, we'll start with vector A, 4, 3, 6, 4, 3, 6, and then we just do our I, j, and k components for vector B underneath, so 1, negative 2, 5, 1, negative 2, and 5. So this is just like a strategy for actually finding out the cross product, because the formula, the algebraic formula for the cross product is kind of like hard to memorize. So doing it this way makes sense. Okay, so we're figuring out our I component, our X component. So we're going to start at I and point down. So we're going to multiply 3 and 5 together. So 3 times 5, and subtract them from this vector here that points towards I. Negative 2 and 6. So negative 2 times 6. So that's our x component. So then we're going to move on to our y, which is j. So 6, 1. So 6 times 1 minus, then we're going to get another line going. So 5 times 4. And then we're going to go with k. So 4 times negative 2. Minus, and the last two, 1 times 3. Okay, and then if we just do all the math involved, alright, so yeah, 15 minus negative 12. So 15 is 12, essentially. Then we got 6 minus 20. And then negative 8 minus 3, negative 11. Okay, I'm really, really sorry if I made any calculation errors. I'm horrible at adding and subtracting, but I think that's good. 15 plus 12, 27. 6 minus 20. And then negative 8 minus 3. Okay, awesome. So that's our cross product between vector A and vector B. And since we already know that if we do it in the opposite way, we know it forms an opposite vector. So I think if we just switched our signs, that would create an opposite vector. So instead of like rewriting it, so this is on top and that's on the bottom, we could just do that to get a quick answer. Okay, so that's how we find the cross product. And we also should note that, I don't know if this will come up, but the cross product is always perpendicular to both of these vectors, which means if we wanted to test if we did it right, I mean, I don't know if you do, but that would mean if you did the dot product between A and what you just did the cross product for, so if you did the dot product between vector A and this new vector that we've done the cross product for, what would you expect the answer to be? So you'd be doing the dot product between vector A and the cross product of vector A and B. So we're saying those two things should be perpendicular to each other. So therefore I would assume it could be 0. So let's try it. So vector A is 4, 3, 6, and this one is that giant number. So dot product, we just multiply them. So we do like 4 times 27 plus 3 times negative 14 plus 6 times negative 11. So I just did the cross product between these two things. Like we could call this vector C. Something that's vector C. Whatever you want to call it. Okay, so let's check it out. 4 times 27, 108. 3 times negative 14, so minus 42, minus 66. 42 plus 66 is 108. Awesome. So that does equal 0. So that's awesome. So that can help you check your answer too. And it should also be perpendicular to vector B. So if you did the same thing, you should get 0. Okay, I'm trying to think of anything else important about the cross product. Okay, I know. I should have set this up here. Did I? No, not really. But the thing that I was saying was cool with the area of the parallelogram. I just want to talk about that for 1 second. So it turns out cross product, the magnitude that results from the cross product is actually equal to the area of the parallelogram formed by these vectors. So if I turn this into a parallelogram, so So that angle would also be 40, and this would be 140, 30, 30, 20, 20. If I wanted to find the area of a parallelogram, I just do base times height. So if I say this is my base here, that's 30. And then my height's going to be the distance at a 90-degree angle. So if I wanted to find my height here, I could use this angle 40 degrees, and I know my hypotenuse is 20, so I can say, well, sine 40 would equal opposite over hypotenuse. So I could say 20 times sine 40 would give me the height, which, as it turns out, 30 times 20 times sine 40 is just equal to the cross product, 385.7. So it's interesting and could be helpful to know that the area of a parallelogram is equal to the magnitude of that cross product, U cross V. So you could extend that knowledge of parallelograms into 3-space. Like, for example, we just did the cross product between A and B. So that was our cross product. So I could find the area of the parallelogram that's defined by these vectors in 3-space by just knowing that it's equal to the magnitude of the cross product. So if I said A and B formed a parallelogram, or we're going to form a parallelogram, and I wanted to know the area of it, well, just knowing that the area of a parallelogram is equal to the magnitude of that cross product. Well, I already know the cross product is this, so if I wanted to find the area of a parallelogram with those points, I could just do 27 squared plus negative 14 squared plus negative 11 squared. So it would give me the area of a random parallelogram. We could use it to find angles between, actually, no, you already know. Okay. Yeah, that's all I got. I guess I'll just say that. You can find the angles between vectors using the same thing we did with the dot product. So doing like the cross product divided by the magnitude of each. So just using that formula, you can find angles in between stuff. I hope this helped you.